Hello. In this video, I will talk about the intermediate value theorem. Let's look at the theorem. Suppose that f is a continuous function on the closed interval from a to b, and let n be any number and value between f of a and f of b. Also assuming that f of a is different than f of b. Okay, that's the conditions. And now, then there exists a number c between a and b such that the value of that c, it will be n. Okay, let's see what this means. When we will take a closed interval from a to b, the corresponding value is f of a here, and the corresponding value for b is f of b. They are different. And now we may say, like roughly speaking, we can say that when we have continuous function cannot skip the values. Okay? Between, of course, we are here between f of a and f of b. Or we can also say that this theorem states that continuous function takes on every intermediate values between f of a and f of b. Okay, I hope we can understand. Let's see. And I can represent n as a horizontal line, because horizontal line, that's the value. And I can draw infinitely many of these lines, any line, any number, n, but it must be the line, the horizontal line placed between f of a and f of b. And now this theorem is telling us for the third time that that line will always intersect that curve, right? Because the curve is continuous curve. Whichever way I will draw it, I can even draw maybe like this, because I have to connect these two dots, because function is continuous. It will always intersect. Let's see where is the intersection. For instance, for that n, it's here, and that intersection will correspond to the x value, which is placed between a and b. It will fall in that interval. Yeah? Let's say that that's my n. Now we can even see, I have the notes below, underneath, n can be taken once, like for my first horizontal line, for the first chosen n, or could be taken more times. So we can see that's the intersection, that's the intersection, that's the intersection for that n, for this horizontal line. And then we have c sub 1, c sub 2, c sub 3. All of these c values, they exist, and they are between a and b. And most of the time, it's really helpful to prove that using this theorem that certain numbers exist. Yeah, we will see. We will apply in a minute for a specific situation that theorem, but we can see we're proving that the number exists. Most likely, we will be not able to find exactly what is c sub 1, c sub 2, c sub 3. However, we will know that it's placed between a and b. And if a and b is a relatively small, short interval, then we can approximate these values. Okay, so that's the existence theorem. We're proving that the numbers exist. Okay, and this is just the wording that I say. The theorem states that continuous function takes on every intermediate value between f of a and f of b. Or we can say, roughly speaking, that continuous functions, they do not skip the values. Okay? One more time, we're talking about the continuous function, continuous scenario. If the function has discontinuity, removable, infinite, or maybe jump, then this theorem is not true. Okay? we need continuous curve. Okay, the same thing. Yeah. And now let's look at this, like how we can apply this. This is one of the common application of the intermediate value theorem. The intermediate value theorem can be used to show the existence of zeros. Zeros are like the x-intercepts for the function, the zeros of the function. Let's see what we can do. If f is a continuous, of course, and takes on both non-positive and non-negative values at the endpoints, meaning that f of a, for instance, is less like negative number or 0, and f of b, the value for the other endpoint, is positive, non-negative, because it's positive or equals to 0. Then intermediate value theorem guarantees that the horizontal line, which in this case is the x-axis, the 0, y equals to 0, will take place for some x's, some c's, because c corresponds to x, between a and b. And it's extremely helpful and useful in a case where we cannot like directly, explicitly solve the function for the x-intercept. But we will know that definitely function intersects the x-axis. Okay, and that's the situation. I can even draw it. Let's try. Let's have the value a, and like it says, let's pick less than 0, f of a. And then the other endpoint, b, greater than 0. I will skip the zeros. Oh, b, f of b. Okay. And now we know that function that we're talking about is a continuous function. I have to connect them. These two dots I have to connect. Connecting them without any gaps, holes, jumps, I will intersect the x-axis. It's no other way. I have to intersect, and that guarantees that this function has an x-intercept, because that intersection, that c value, is the x-intercept. We may not have the explicit solution, we may not have the exact value, but as soon as we can try to narrow that interval, maybe we can approximate really well. Okay, but this definitely guarantees that the zeros, the x-intercept, exists. Okay. Because the n value, or maybe I can draw that n value is actually that 0, because x-axis represents to the y0. Yeah, that's the horizontal, that's the 0, value 0. And 0 is between f of a and f of b. Okay, let's do example number 1. Show that there is a root of an equation between 1 and 2. And equation is the third degree polynomial equation. 4x cubed minus 6x squared plus 3x minus 2 equals to 0. Okay, that's me what I can do. I can name this left-hand side of this equation as a function f of x. And I want this function to be 0, okay, to intersect the x-axis. Between, yes, to have the solution on the interval between 1 and 2. Okay, what we can try to find what is the corresponding value for 1 and what is the corresponding value for 2. I'm really hoping that one of them will be positive, one of them will be negative, meaning one of them will be above the x-axis, one of them will be below the x-axis, and 0 will be our n value, horizontal line. That will be the guarantee. Okay, let's substitute 1. 4 times 1, 6 times 1, 3 times 1 minus 2. Okay, what we have? We do have 7 minus 8, or we have negative number. Now let's substitute 2. 4 times 2 cubed, 8. 6 times 2 squared, 4. 3 times 2, 6 minus 2. Okay, what we have? We have, we do have 32. We do have 24. I hope my arithmetic, and let's say 4. Negative 20, I think it's 12. I hope. Okay. Definitely negative 20. Definitely it's a positive. Yes, it's a positive. Positive number. Did I make some arithmetic mistake? I hope not. Negative 20 minus 32, 12. Okay, it means one number is below, one number is above. This is the guarantee that function will definitely cross the x-axis. Okay, let's put 1. The value for 1 is negative 1. And value for 2, of course, please ignore my labelings are correct, just the scale. And now I don't know how function looks like, but I know that I will definitely intersect at least once. Yeah? Maybe twice, yeah? maybe even 3 times. We don't know, but that's not the case for this situation. This function is definitely continuous function because polynomials are defined everywhere and they are continuous, yeah, on all of the real numbers, and connecting the numbers below the x-axis and above, we will intersect at least once. And this is the x-intercept. Yeah, definitely the C exists. The solution for this equation will be the value C. Okay, and it's definitely in the interval between A and B. Between 1 and 2, don't be general. Yeah, between 1 and 2. Maybe, I don't know, maybe 1.5, maybe 1.1, maybe 1.9, but definitely the number is definitely the x-intercept, the root of this equation exists between 1 and 2. Okay? Just because of this and continuous function. Yes, continuous function. This expression, this is continuous. No, my continuous function. Okay, because it's polynomial. Okay, let's solve another example. And that's the solution. Oh, okay. Multiple choice. According to the intermediate value theorem, which of the polynomials below must have a real root on the interval from -1 to 0? Okay, so this one is, we have to actually treat each of this function as a polynomial, and we have to check how the values behaves at -1 and 0. Okay? We know that only one answer is correct. That's always the case. Okay, I mean, it's a little bit time consuming. What I can do, I can call it the options A, B, C, D, E as a function. That means the first function is A. I will check A at -1 and I will check A at 0. Okay? A at -1, and that's, of course, that's the A of X. And this will be B of X. This is C of X. And so on. Okay, let's substitute -1. -1 cube is -1, then -3, -3, -4. I don't even have to do the arithmetic. This is definitely a negative number. And then when we substitute 0, which of course it's funny, it's also negative. That means this intermediate value theorem is not giving us the guarantee. That's not a good number because it might be, yeah, this is -1, this is 0, and both of the values are negative. One of them is lower, one of them is a little bit higher. And that's the corresponding values. And they might intersect the x-axis, but they might just, the function on that interval, we may just connect them this way. Yeah, that means that's not a guarantee that we will go above the x. We will intersect the x-axis. We will not have the root. Okay, let's do the same thing for b. Yeah, that means it's just, oh no, I don't want to erase. We have to just check the functions. Okay, b at -1, b at 0. b at -1 is 1 minus 3 minus 3 minus 1. Of course, negative number, less than 0. When we substitute 0, it's also both negatives. Yeah? That's not a guarantee. We're looking for one positive, one negative. Okay, c at -1. -1, +2, -4, -1. Oh, it's getting now, it's still negative. And c at 0, you can notice it's also negative. Both negatives, both below the x-axis, that's not a guarantee. Okay, d at -1. -1 plus 2 minus 4 plus 2. It's less than 0, yes, -1. And then d, not b, d at 0, it will be 0, 0, 0 plus 2, greater than 0. We do have two different signs in the corresponding value. One of them is below, one of them is above. All right, we may actually get the exact value. This will be -1, this will be 2. And we may double check the function e, but I will assume that this is, I think both will be positive, and both values will be positive. I mean, just to e at -1, yeah, just to double check, because we never know, maybe we make the arithmetic mistake. This will be -1, -1, oh, +2, -4, +5, 7, 6, that's positive number. And at 0, we will have 5. Okay, that's mean both positive, that's also not good. Okay, D is the good answer. And we may just draw it just to prove it. On the interval between -1 and 0, the corresponding value for -1 is -1. For 0 is 2. Okay, and we will definitely connect that function. Okay, let's call it d of x, and this is the root. This is the real root, the intersection. Okay, so that's the use of the intermediate value theorem. Okay, another one. Oh, let's check. Also multiple choice. One option is correct. Let f of x be continuous function on 5 to 10. The value at 5 is 1, the value at 10 is 4. Which one of the following statement must be true? Okay. Before we start reading, we may try to picture this scenario. Interval is between 5 and 10. Value for 5 is 1. Value for 10 is 4. Okay. And we have continuous function. Let's draw this function. The easiest way is to do this. Right? That's the easiest, but maybe we can try to do slightly, maybe something like this, a little bit, yes, a little bit different. Okay, now let's read. F of x, yes, the first one, f of x equals to 3. For f of x is equals to 3 for some values of x between 5 and 10. Okay, that means 3. This makes sense because 3 is the value between 1 and 4. That means it could be between 1 and 4. F of A, F of B could be my n value. Okay, I can draw this. This is n equals to 3, and the corresponding x is, of course, it will be placed between 5 and 10. I mean, this looks like intermediate value theorem because 3 is the value between 1 and 4, and the corresponding x falls between 5 and 10. Yeah, that's definitely true, but let's eliminate the other one. F of the B, the option B, is telling us that the intermediate value 3 will have x, the corresponding x between 1 and 4. No, 1 and 4 is the y values. That means that's definitely incorrect. That's wrong. F of x equals to 7. Could be the situation, but 7 is not the intermediate value. The value is outside. It's not between 1 and 4. That's wrong. This was the problem. And again, that's the problem. F of 7, no. And that's even not the x values. Okay? We have to figure out the distractions. And the last one is interesting. F of x equals to 1. Yeah, we may have the value 1. I mean, I can draw the number, the line 1. Yeah, this is 1. I can say 1. If the f of x equals to 1, if and only if x is 5, because that was the given value, the end one of the endpoint, 5. But you may notice we also have another intersection. Like let's say C sub 1. That means not only the horizontal line f of x equals to 1 will intersect the curve at x equals to 5. We may have other values, and we may even have more. I just draw it 1, but if the function is like a higher degree polynomial, we may even have more intersections. That's definitely not true. Not if and only if. That's not the case. Okay, we proved that that's the correct. The A is the correct statement. Okay, another one. Let's look at this example. We might use the calculator for this because it's a good use of the intermediate value theorem. But let's see. Show that the function f of x equals to cosine square of x minus 2 sine of x over 4 has a 0 in the interval between 0 and 2. And then we will try to use something that is called bisection method, and we will find the subinterval, smaller interval in that 0-2 interval. And actually they asking us the length of 1/8 that contain that interval that contains a 0 of this function. Okay, so we can see function is a little bit, the formula, it's a little bit crazy. We will probably not even know how this function looks like exactly. It's trigonometric function, but cosine square of x minus sine x over 4. Okay, that's a little bit crazy. But first of all, let's check this. We will find the values at 0 and value at 2. Right? That's we have to substitute instead of x 0. 0 over 4 will be 0, and we need this value. This one is probably not complicated because cosine at 0 is 1, 1 squared is 1, and sine at 0 is 0. Okay, but then we have to substitute 2, cosine at 2 squared, and then sine at 2 over 4 is 1/2. We can get cosine and sine at 1/2. Yeah, that's, oh no, no, because that's the radians, that's the radians. We know sine of a certain angle is 1/2. Oh no, no, that's all of the radians. That's we have to put these values to the calculator, and I did this, and I got negative 0.0786. We can see the good thing is one number is positive, one number is negative, above the x-axis, below the x-axis. Okay, how can we organize our work? Let's draw this. I don't know how exactly function looks like, but maybe something like this. At 0 is 1. Okay, this is our function f of x, and at 2 is negative 0.8, 0.786. Yeah, okay. So one value is below, one value is above. Definitely that x-intercept, that 0 exists. Okay, I can call it C. That and this will be the 0. That's the 0. X equals to C. But now maybe the interval between 0 and 2, it's too wide, too long. Okay? We will try to get smaller intervals. So maybe I can try interval between 0 and 1. However, they want 1/8. The length of the interval 1/8. Okay, at the moment I have 1. So from the interval, from the length between 0 and 2, the length is 2. Between 0 and 1, the length is 1. Okay, value for 0, we know that is 1. Value for 1, I use the calculator and I got negative 0.0203. 1 positive, 1 negative. So now I can, I kind of draw it at the center. Let's maybe do, because let's do this. Okay, that means between 0 and 1, the intermediate value theorem, it's also guaranteed that we have, I mean, that root is between 0 and 1. Yeah? Between 0 and 1. Okay. Now let's maybe take 1/2 and 1. Right? We may pick any interval. If it doesn't work, we can move it to the other. Oh no, between 1/2 and 1, because then we will have, if this works, we will have the length 1/2. Between 1/2 and 1. Value of the function for 1/2, I use the calculator and it's positive 0.521. Positive, and we do have value for negative, for 1, it's negative 0.2. Okay, we can notice, oh, hang on, let's put the value for 1. For 1 is negative 2, I mean negative 0.203. Value for 1/2, it will be, actually, yeah, it's 4. Okay, that's we make, yes, we narrow, we make the interval smaller. Between 1/2 and 1, definitely that C, that intersect exists. Okay, what else we can do? We can do 3/4 and 1. Okay, that's when 3/4 will be somewhere here, 3/4. I don't know, because my graph is just like like a picture, like a draft. We don't know exactly. But if I take a 3/4 and substitute instead of x to the original function and use the calculator, it's positive number. Positive 0.163. Positive, and value for at 1 still stays the same, negative. Okay, that's we are here. It's still good, or a little bit lower, but let me put the approximation. Okay, so definitely the intermediate value theorem guarantees that the root, the 0, is between 3 quarters, 3/4, between 3/4 and 1 on that interval. And I think I have what I did. 7. I think I put 7. Where is, let's keep this and let's maybe move 1. I think I put 7/8. Yes, because this is 3 quarters, and then 7/8. Yeah, if we will take the interval 7/8, it's 3.5 quarters. That means I hope, yeah, 7/8, because when I've tried, of course, couple of values. This is interval 3 quarters, and the, oh, what I did, and this will be 7/8. Oh, too tiny, too low, actually. That's F. Okay, 3 quarters, we know for the 3 quarters is positive 0.163, but 7/8, when we substitute instead of X and use the calculator, it's negative 0.002. Okay, that means it's just below the X-axis, negative 0.02. Okay, and we did prove that between, let's maybe do zoom. This will be 3 quarters, and this will be 3.5 quarters when we simplify to the same denominator, and that's the value C. And the length of an interval. Oh, actually, it's even. No, it is 6/8, 7/8. The length is 1/8. That's what. Oh, too fast. That's what we supposed to do. And just one more time, this value is 0.2, and this value is negative 0.02. Okay, but we see we can see the idea, always proving that one value on the given interval, the initial value is above or below, and the terminal value is also has the opposite sign. One value below the x-axis, one value above the x-axis, and connecting these points with intersecting x-axis, and that's the proof that the 0 exists of the given function or the root of the equation. Okay, you may redo all of these 4 examples and you will definitely understand the intermediate value theorem. Thank you.